So let's look at some examples of writing out these ionic equations. So I have calcium chloride, cesium sulfate. Now the first thing I need whenever doing this is I need to get my molecular equation, which means I need to predict the formulas of my products. I then need to pick the phases of my products, and then I need to balance the equation. Once I do all that, I end up with calcium sulfate and cesium chloride as my product formulas. Calcium sulfate, that's going to be a solid based upon those solubility rules. Cesium chloride is going to be aqueous based upon those solubility rules. And then I need to balance the overall equation. To do that, I need a 2 in front of the cesium chloride. Next, I'm going to write the complete ionic equation, which means I'm going to break everything up into its ions. So I take that calcium chloride, the CaCl2, and I get 1 Ca2 plus, 2 Cl minuses. We don't write Cl subscript 2 minus. No, that subscript tells us we have 2 chloride ions, so I need to put a 2 out in front of the Cl minus. And then I have it plus the 2 cesium plus 1 ions. I have 1 sulfate ion, and that's going to form the calcium sulfate solid. Remember, solids, liquids, and gases I don't break up. I only break up things that are aqueous. Plus the 2 cesium plus 1 ions plus 2 chloride ions. Once I've got the complete ionic equation, I want to get the net ionic equation. That's where I want to remove the spectator ions. In order to remove spectator ions, I have to have the same ions on the reactant side as I do the product side, and I have to have equal numbers of those. So my net ionic equation for this, calcium 2 plus an SO4 2 minus, goes to form the calcium sulfate solid. That would be my net overall ionic equation. What is this showing? It's showing me that when I mix those two aqueous solutions together, the only thing that happens is the calcium and sulfate come together. The cesium and the chlorides are still present in solution, but they're not actually doing anything. They're not changing. So this is the overall net reaction that's going on. All right, let's look at another example. So I've got sodium hydroxide plus cadmium nitrate. So again, I need to predict the formulas for the products first. Then I need to predict the phases of those products. Then I balance the overall equation. So doing that gives me the molecular equation, and I end up with this balanced overall molecular equation. Now I can write the complete ionic equation, so everything that's aqueous I break up into its ions. And in doing that, you can see I end up getting everything broken up into its ions form. Now I'm going to remove the spectator ions. So remember, any ion that's on the reactant side and the ion is present on the product side, I can remove those. Also keep in mind they have to be the same amount of them. When I do that, to get my net ionic equation in this case, everything cancels. Because everything cancels, I have no reaction going on. So I write NR. That's how I represent no reaction. So what is that telling me? Well, it's telling me when I mix this sodium hydroxide solution with this cadmium nitrate, I'm just creating a new mixture. I'm creating a new solution that's got those ions present, but there was no chemical reaction that occurred. All right, let's look at another form of this. So I take aqueous solutions of sodium phosphate and magnesium chloride and mix them. I want to write the ionic equations for this. Well, that means I have to be able to take the name and write the formula to begin with. So you have to know naming rules and everything else. It's very important. So taking the sodium phosphate and magnesium chloride to get the balanced formulas for those, I get the Na3PO4 and the MgCl2. Now I need to write an overall molecular equation, so I'd have to predict the products from those two combining together, predict their phases, and then write the balanced equation overall, and I get this. Now I want to break these up into their ions to get my complete ionic equation. So when I look at the sodium phosphate, once I break these up, I get this equation. Now in looking at this, let's go through this because this is a little bit trickier. Notice I've got a 2 in front of my Na3PO4. Well, when I break those up in the ions are Na plus and PO4 3 minus. For each Na3PO4, I have 3 Na plus ions. But the coefficient of 2 out in front of that in the balanced equation means I have 2 Na3PO4s, which means I have 6 Na plus ions. So you've got to take into account those coefficients as well as the subscripts. All right, so I end up with 6 Na pluses, 2 PO4 3 minuses. I get 3 Mg plus 2s, 6 chloride ions, and then on the product side I get 6 sodium ions, 6 chloride ions, and then I don't break up my magnesium phosphate. So now I want to remove spectator ions to get my net ionic equation, and there is my net ionic equation because the sodiums and the chlorides are going to cancel out. Again, it doesn't mean the sodium chlorides suddenly disappear. They're still present in solution. They just didn't take part in any sort of chemical reaction. All right, another example of starting with the names first. So I've got copper 2 chloride and potassium nitrate, which gives me these formulas. Get my molecular equation, predict the products, predict their phases, balance the overall equation. I end up with this. Break everything up into its ion forms, and then cancel out the spectator ions to get the net ionic equation. Well, everything is aqueous, so overall I have no reaction occur. Now, simply because everything is aqueous doesn't mean I can't write out a molecular equation and a complete ionic equation. You can still do those steps even though you're not going to have a reaction overall. All right, the last thing I want to look at when dealing with precipitation reactions, I want to look at a basic calculation that's going to be fairly common when dealing with these aqueous solutions and precipitation reactions. So if I take 25.1 milliliters of a 0.102 molar silver nitrate solution and I react it with excess 0.0723 molar magnesium chloride, first I want to decide, is a reaction going to occur? And then secondly, since I'm dealing with precipitation reaction, if a reaction does occur, what solid is going to be formed? And then lastly, I want to know what mass of the solid could I expect to have. So first, does a reaction occur? And what solid is formed if it does? Well, I need my overall balanced equation. So I need to predict my formulas for my products, predict their phases, and then balance it, and end up with silver chloride solid. Okay, so I know a reaction occurs, know what my solid is. Now I want to figure out what mass of that solid is formed between these two reacting together. Trying to figure out how much silver chloride solid was formed when these two are mixed together. The only way I can do that is I need to get things to moles first, because I'm starting with the silver nitrate solution. I'm trying to get to silver chloride. The only way I can convert between those two compounds is through a mole-to-mole ratio based upon that balanced equation. So how do I get moles out of a volume and molarity? Well, I start with my volume, convert the milliliters to liters, use that molarity to convert between liters and moles, and I end up with the 2.56 times 10 to the negative 3 moles of silver nitrate. Now I'm trying to figure out what mass of the solid was formed. Well, since I know the moles of the silver nitrate now, and start with the moles of silver nitrate, using the balanced equation I can convert to moles of the silver chloride. Remember, that's the solid. And then I can use molar mass to convert from those moles of the solid to grams of the solid. And I end up with the 3.67 times 10 to the negative 1 grams of silver chloride solid. So you have to get used to using these volumes and molarities now with these aqueous solutions as starting points to determine amounts of products or reactants or whatever. Okay? Whereas previously in previous examples we started with grams and went to moles. Now we're starting with volume and molarity going to moles. Alright, but that's going to be it for precipitation reactions.